There's a lot of discussion today about the environmental impact of what we do in all aspects of life. There was a study done by the UN that shows that the airline industry contributes about 1% of the overall global carbon footprint, and concrete between 5 and 8%. So building with mass timber or solid wood construction is certainly one very effective solution to help curb this increase in carbon. Mass timber or solid wood construction really refers to a new way to build with large wood panels made with engineered wood products. There are different panel types available, and CLT is one of them. Generally speaking, there are two different main types of panels. There's the edge laminated, meaning that we put the planks side by side, and there's the cross laminated, where we build layers with planks at 90 degrees to each other. And each of these categories can either be glued, nailed, or doweled. So that gives you 6 basic solid panel types. In North America, we have also used engineered wood products that are usually cut up but originally fabricated in large panels, and that includes LSL and LVL. Mass timber really offers an interesting alternative to what would often be a concrete construction. You typically can achieve much more robust structures that will perform in a way that would be considered comparable to concrete construction. L'école au cœur de l'île, which is built for the British Columbia Francophone School Board, is a project that came online just before CLTs became available in Canada. One cost-effective product that was available was glue-laminated timber on the flat. Essentially, it's like giant tongue and groove. The school is quite large. So from a code point of view, the building needed to be non-combustible. So in that case, we elected to build the floors out of precast concrete and then the roof structure with post and beam and solid wood planks. ESB is a 150,000 square foot building at the University of British Columbia. The project was chosen as a demonstration project. There was an opportunity there to include quite a bit of innovative elements. It is essentially a 5-story post and beam structure, solid wood panel construction. The post and beam itself are executed in this building with modern connection materials. The idea is to limit vertical shrinkage by ensuring that the columns are continuous throughout the height of the building. And we used a new connector from Austria called the Sherpa connector to connect the beams to the exterior columns, pocketed the interior columns to let the beams through and create continuity for the columns above through a steel pedestal. The other element of innovation in the building was the chevron braces. Laterally, the building is supported by 3 concrete cores, but at one end, we wanted a more open structure and used a CNC-shaped glue-lam brace element, which is exposed. We developed an approach to achieve a fairly high degree of ductility in those braces. So we shaped the glue-lam using 5-axis CNC and then used tight-fit pin connections, which are visible. The critical issue technically is to space those tight-fit pins to ensure that they yield and provide the ductility that was assumed in the design. The next innovative element are the transfer trusses. The entire ground floor of the timber wing is spanning across theater bases, which run the full width of the building. So we have 4 stories of construction, which are transferred at the second level. And the difficulty there was that the trusses needed to remain quite open because of circulation and future flexibility. So the trusses are essentially a combination of Vierendeel and diagonalized trusses, quite open, but spanning 19 meters and carrying 4 stories of construction above. We were able to achieve sufficient strength and stiffness by, again, using the wood concrete composite construction that we were already using in the floors. So the truss cord is a wood concrete composite T-shape. At the bottom, we had to use a steel element, but again made it composite with the concrete floor, and this way achieved sufficient stiffness to transfer the building. The last and I think most interesting element in the building is this stair in the grand lobby. The architect's vision was that that stair was going to serve as a meeting point for the different occupants of the building. The architect chose to locate an oversized stair that could become a point of interest. The original concept that they drew was for a fully cantilevered stair. It has been done in steel and concrete before, but had never been done in wood. We again used the proprietary German connector called the HSK. And with the help of Leander Baton, who invented the system, we developed some connections that could achieve enough rigidity to fully cantilever that stair from the floor supports. current engineered wood products are, on a weight to strength ratio, very favorably comparable to reinforced concrete. From a pure structural point of view, it's just a matter of resolving the issue of how it's going to be assembled. But there is no doubt in my mind that we can achieve heights that may reach or exceed 30 stories. It's a matter of developing methods that will be effective and testing those methods, of course. We recently did a comparison where we had a standard steel beam and steel deck and concrete solution. We had a hollow core solution and a wood concrete composite solution using CLT. And the costs were really at about the same level, but you're not really just comparing costs, you're comparing value. On the sustainable side, of course, wood sequesters carbon as opposed to producing carbon, but also thermally. Wood, of course, has a much higher R value than either steel or concrete. The lightness compared to concrete, wood is about a sixth of the weight of concrete, and speed of erection. CLT brings a number of advantages that other materials don't have.